operation. And a student, okay? A student, when they get up in the morning, may not change their shirt, okay? that's a student behavior. So they all have this getting dressed process or method, but the behaviors of that method are different, specialized to the individual derived class. So think of this as a base class, derived class, and derived classes. So for the soldier, contains some gear, whatever the gear is, okay? This gear is a container for things, you know, rations and so on, weapons and whatever. And all these officers have that container for gear, but they may put different things in it. And they all have this salute method. If I pass a soldier by pointer or reference to a function, if a function accepts a soldier by pointer or by reference, then if that soldier class has a salute method, inside that method, if I call salute, all of these objects will react to the salute, but in a different way. And that method, because it accepts a base pointer or reference, a soldier pointer or reference, it applies that salute method to each one of these. So I can write a function that manipulates soldiers without caring what kind of soldier I have. Is this a sergeant? Is this an officer? Is this a private? I don't care. You know, some functions I may care, but in this particular function, I don't care. Okay? So, so if in that method I call salute, if I pass it a private, the private says, yes, sir. Snappy salute. And I pass him a general, the general says, as you were, private. Okay, casual. So same thing, they're both saluting, but they each do it in their own way. They've modified the behavior. So that's what inheritance is all about. There's actually some code behind this. I wrote this little example for a short course I taught a couple of summers ago. And you can look at it and see how it works, but simple idea. Now, the reason that I can pass any derived class where I'm holding a base class or pointer and have it correctly operate correctly is because of this virtual function pointer table. Every class that has a virtual function has a virtual function pointer table. And so here I have a base class that defines virtual MF1, MF2, and a virtual destructor. These are all virtual functions. And the derived class D does not declare an MF1, but it does MF2. Now MF3, it adds this MF3 function that B didn't have, and it has a virtual destructor. So what happens here is I have, for the base class, a virtual function pointer table that has a pointer to MF1 and a pointer to MF2 and a pointer to the destructor, all for the base class. So if I have a pointer to a base object, that base pointer points to the base's virtual function pointer table, and when I call salute, okay, it goes to the base's salute. Now, the derived class, I have a virtual function pointer table that includes MF1, even though the derived class didn't mention it. It includes MF1, MF2, and the new MF3, and the destructor. And so now the pointer to MF1 goes up here to the base because this guy has an MF1, he just didn't declare it. That means I'm going to use the base's MF1. That's what that means. And so his pointer to MF1 goes up to the base class. He provided an MF2, pointer goes to the derived MF2, pointer to MF3 goes to the derived MF3. So let's assume that method 2 is salute. Okay? So now, if I pass a, notice that this derived object I'm pointing to with a base pointer, and I can do that. So this is a pointer holding the address of that object, but it's typed as a base pointer. So now, this function in which, when I call salute on that base pointer pointing to a base object, MF2 is going to go to the base's MF2. When I call salute on the derived, even though this is a base pointer, I've got this derived object, okay? So I go to, here's my salute function, I go to the derived salute. So I'm going to get the correct behavior even though the function is declared to take a base pointer or a base reference. So what that means is that I can write a function that I want to operate across this inheritance hierarchy. I want it to behave correctly, okay, but I don't know what's going to be passed to me, so I just use, in that function, I just use the base class protocol, and it'll work correctly whether I pass it a base object or a derived object, okay? Notice that my base object has a pointer to the base virtual function pointer table. The derived object has a pointer to the derived object's virtual function pointer table. That's why we dispatch the salute call on a, so I have base pointers in both cases, pointers that are type base, but when I call salute, I'm dispatching to the base salute if this is a base object, but if I point to a derived object when I call salute, I'm dispatching to the derived salute. Okay? It's called polymorphic dispatching. Okay. Now, one other thing, because this is a base pointer, I can't call MF3 on this derived. I'm pointing to this derived up. Why did you do that? I have no idea why you did that. Okay. So I'm pointing to this derived object with a base pointer, but all the base pointer understands is this base protocol. The compiler won't allow me to call MF3 using that base pointer. It'll say MF3 is not defined for that base pointer. Now, I can call MF3. What I have to do is I can take this base pointer and I can do a dynamic cast. And what dynamic cast does is it looks at the pointer's virtual function pointer table, and if I cast it to a D pointer, it looks at, and if this pointer is bound to a D object, it'll just give me that same address, but typed as a D pointer. And now I can call MF3 using that D pointer. So I just say D star pointer equals dynamic cast of B star, of this pointer, okay? And as long as I really am pointing to the type of object that I'm casting to, I just get the same address, but now typed as the new type. But if I'm not pointing to that derived class, if I'm casting to a sergeant and I'm actually pointing at a private, okay, then the dynamic cast returns 0 for the address, and I have to check it. But this guarantees that I won't attempt to go call a method on a class that doesn't have that method. If I were allowed to call MF3 on this base object, what that means is MF3, I would just step down here and try to execute a method in this garbage. I would go off in some garbage location, get a memory fault violation, and away I go. So, if you go and interview for a C++ job, This will be, the virtual function pointer table will be the third question they'll ask you. Okay, guarantee you. If you can't answer that, thank you, we're done. Okay. If you can't answer it, they'll smile and they'll start to ask you harder questions. You know, it's their job to ask you a question you can't answer. You know, you don't get blown away because you can't answer a question, but you sure want to be able to answer a question about virtual function pointer tables. And I'll ask it on the exam too. Maybe not directly. I won't say the virtual function pointer. I'll say some question that forces you to know, you know, about the virtual function pointer tables. Okay. Mental model. This is all mental model stuff. But you're starting off with a really good mental model. So now here's class relationships. So there are only 4, actually 4.5. And it's surprising that those few relationships are all we need to write into the software we're ever going to write. Okay? So we have inheritance, which is a relationship. So we say that a general is a soldier. A private is a soldier. If you are considering using inheritance, don't use it unless you have an is-a relationship. Ask yourself, is this an is-a relationship? Okay? So D is a B. The derived class is a base class. A specialization, but it is. Composition, ownership of P, part of. This is a very hard relationship, and we write this in C++ this way. C# and Java lie to you. You write members in the base class just like this, but they aren't compositions, they're aggregations. Okay? I'll come back to that in just a second. So this is really important. This says that P always, when I construct a C, I always construct a P immediately. I don't get to use the C object until P exists. When the constructor for C returns, P exists. Guaranteed. The language guarantees it. I'll show you why this morning. Aggregation is a weaker ownership. A aggregates the part P, so this is composer composes part P, aggregator aggregates part P, and this is a part of, but now P doesn't exist until somewhere in my code I call new. All right? So that means that I may construct the aggregator and never have that part. So this is really maybe a part. This is always a part. So in C# and Java, a lot of people talk about composing user-defined instances, and they're lying to you. That isn't composition, it's aggregation. A lot of C# and Java programmers talk about composition when they really mean aggregation, and it's important to make a distinction. We'll see this morning in spades what. So this is composition in C++ written this way. This is aggregation in C++ written this way. Aggregation in Java and C# is written that way. In Java and C#, this is aggregation, because you have to call new to create that instance on the managed heap. Okay, this is a using relationship, not an owner relationship. So in this case, you did not create R. Somebody else created R and passed it to you. So it might be in some function like this. Here's a U function, register R. So somebody else created the instance of R and passed it to you to use. And so what that means is that you should not destroy, not delete, not destroy, not make invalid that object because it doesn't own it. It's just borrowing it. For relationships. Now, there's another diagram that talks about the same thing, but it's a pictorial view. So now here I have a composite object. So D inherits from B, which composes C, and D uses U, and the client aggregates D. Now in memory, because B composes C, C is literally inside B, and I'm going to prove that to you this morning. It literally is in the footprint of B. And B, because D derives from B, D literally has a B in its footprint. It's there. So when I constructed D, the language has to support immediate construction for B because B is part of C. And when it constructs B, it has to immediately construct C because C is part of B. So we're guaranteed, if I constructed D, I've constructed a B, I've constructed a C. And before I ever get into the curly braces of my D constructor, the C object exists and the B object exists. Yes. And here's the uses. It isn't inside anybody's footprint. This guy didn't own it, doesn't own it. The aggregator, this guy isn't inside the aggregator's footprint. Okay. This diagram is supposed to show memory residency. It's sort of a, really you could, memory is one long line probably, but this is just to make it really clear about the inclusion. This is a really important diagram. You want to remember this. You really do. Okay. So now I want to go here. I've got to go, this tells me it's in the handouts repository, CPP class relationship. If you look on the college server, it is. I forgot to synchronize my machine in the last couple of days, so I don't have it there, but I do have it some other place. So let's go, let me grab it from where it is in SU, Core Technologies, CPP, code. So don't you go there, you go to the repository, you go where the link tells you to go. But let's look at, after class relationships. Class relationships. Okay, so now, here's my relationships.h. So I have a class C. So this is just like the diagram. I have a class C that's going to be composed by B. I have a class U that's going to be used by D. I have a class B that composes C and is the basis for base for D. And here D is derived from B and uses U. Okay, and the code, what's in those functions doesn't matter. It's just silly little demos. Doesn't do anything. I have a constructor that constructs nothing. I have a destructor that destructs nothing, just to show you this. But here's what we want to do. Let's just run this. So here, the guys are running, and now the code is analyzing this and printing it out. Now we'll look at the code that does it in a minute. Location of D is from 1703.624 to 1703.636, 12 bytes. Code B, location of B, is from 1703.624, same as that, to 1703.62, less than that, 8 bytes. Inside! Okay? So B is inside D. I just proved it to you. Okay? No argument. It's inside. Okay. So now, location of C is from 1703.628, less than that, to 1703.622. So it's inside D, and it's also inside B. 1703.628. So it's inside that. So it's just at the end of the B class. So C definitely is inside B. Why didn't it start at the beginning? Because the beginning was a pointer to the virtual function pointer table. That's what that extra space was, pointer to the virtual function pointer table. Why didn't D have the extra space? Because that slot for the virtual function pointer table just has a different address. It's the same in memory, same thing, but it's a different address. For the D object, it's pointing. Okay. So, and the location of U ain't in there because it's using. So we've just demonstrated incontrovertibly that that picture is correct. Yes! That's a really important mental model. So again, what you know now is that when I constructed D, I'm guaranteed to have constructed a B, and that happens before I ever get into the curly braces inside the constructor of D. I've already constructed B. As soon as I make the transition from my calling argument into the curly braces, in that little interspace, in that little interstitial place, I constructed B, and B constructed C. Then I get into the body of my constructor. That's the way it works. Yes? So if you're interested, we can see how we do that. Here's the relationships.cpp. And here's the show parts. This is where I'm doing it. So what I'm doing is I take D star this. So start of D, this pointer points to the top, okay? And I'm doing a reinterpret cast to size T, so I get this in a form that I can print out, okay? I'm just making it printable in a convenient way, okay? And then end of D is start of D plus size of contents of this. Remember, I'm inside D when I'm calling this, okay? And same thing for, same thing for B, and so same, okay? Here, I am still inside D, but now I'm casting this pointer to B. That just moves the pointer down to the B part, okay? That's what it does. And then, so that's how you do it. Just in case you want to measure how things are laid out in some class that you're building. So, yes, it works, yes. Oh, I'm so excited. I'm going to skip the compound object creation. This is really important, and we're going to talk about this. I'm going to talk about it on Thursday. So, Naga, you have a job. Thursday, when we start class, don't let me forget, the first thing we're going to do, at least one of the things we're definitely going to do on Thursday, is to talk about the compound object creation, okay? But now I want to go to this hierarchy presentation. By the way, here I have demonstrate composition, demonstrate inheritance, and I would like you guys to look a little bit at that code, because on Thursday, if we have time, we're going to walk through this code. And it'll be a lot more effective for you if you've looked at it before we talk about it. Okay? All right. Hierarchy presentation. So some definition I'm going to skip over. You're invited to read them. So parts of these, I'm going to skip over a lot of the words and mostly look at diagrams. I think it's a good idea for you to go back and look at the presentation and read all the words. Okay. So compositions are special associations which model a part of or contained, and they're represented with these solid diamonds. So class X composes class Y and composes class Z, and it's written this way in C++. In Java and C#, it's written the same way, but it only applies to value types. Primitive types and structs is the only thing it applies to. Okay, so we say X contains Y and Z, or Y is contained by X. Y is composed by X. X composes Y. Here's the aggregation. We show aggregation with a hollow diamond, and now class X has a pointer to Y and a pointer to Z, and sometime later we'll construct them. If I construct them in the constructor, its behavior is getting a little closer to composition, but it's still not composition because that object exists before I initialize Y and Z. But if I was composing, Y and Z exist before the X object is completely formed. Normally, we use aggregation because we may never create it. We may need it in some particular member function, for example. Maybe we're using it in a couple of member functions, and that's the only place we need it. And so if we don't need it, why spend the CPU cycles to construct it if we're never going to use it? So we wait until we get to that method, and then we construct it. And in this case, if we're pointing to it with a pointer but constructed in some method, almost certainly that means we're going to use it in more than one method. If I could construct a local object in the method, if it's only used in that method, I don't need to have it here. It's still aggregation if I construct an object. So here, the classic model is I'm going to call new. I'm going to create on the heap using these pointers. That's a classic model of aggregation. But if I construct a local data member, an instance of some type, inside a function, just declare it and use it, and then when that function goes out of scope, it's gone, that's aggregation too. Even though syntactically it doesn't look like aggregation. It is aggregation in the sense that this object is part of the behavior of the aggregator, but doesn't live for the whole lifetime of the aggregator. Okay, so hierarchy via composition looks like this. So now the composed object, like we said, is inside the composer, but its public member functions are not part of the public member functions of the composer. So the composer gets to use these public member functions, but a client of the composer doesn't. Client of the composer never sees it. So this composed object is just more private data. Okay? Other private data, this particular piece of private data, and some private functions. And I would have private functions if they need to do something that requires design knowledge in order to use correctly. If you look at my datetime class, you might have seen a ctime function, private function. It was there because you really have to understand the design a little bit to use it correctly. So I made it private. Okay? And the public functions may use these to implement their behavior, but these public member functions shouldn't force you to understand the complete design of the object. So composition is a part of. We've already said most of these words. Let me skip over. There's some demonstration programs. That's the ones I just pointed to at. We're going to go over them on Thursday. Here's an inheritance relationship. So class X, class Y, class Z. Notice the public. In C# and Java, there is no public. It just says class Y : X. Because there's only one kind of inheritance in C# and Java, and that's public inheritance. In C++, there's public inheritance, protected inheritance, and private inheritance. Almost always we use public inheritance. I've written thousands of programs using inheritance. Over my 50 years of programming, I've written thousands of programs that use inheritance. I've probably used non-public inheritance 4 or 5 times out of those thousands. Okay? We don't use it very often, but every now and then, when you need it, you need it. Okay. So here's what that looks like schematically. Now, this guy, this base class, here's the derived class, here's the base class lies inside the derived class, and I'm showing you its public member functions are public member functions of the derived. Remember that is a discussion. So when I pass a soldier to this method that's going to call salute, every one of those derived objects has to have the salute method. And I could call some other method. Any method that the base class provides, I have to call on every single one of those. So that says those methods have to be methods of the derived class, and they are. The language supports that. There are constructors and destructors and assignment operators are not inherited. Everything else is. Whether it's private or public, it's inherited, okay, but only the public member functions become part of the interface of the derived class. Okay. Now, here is a diagram that talks about the three flavors of inheritance in C++. Public derivation, protected derivation, private derivation. So public derivation supports an is-a relationship. Public members of the base class become public members of the derived class. Yeah. And you say, how about constructors and destructors and assignment operators? Well, they aren't inherited, but the compiler will always generate them if you need them, guaranteed. And so they are members of the derived class. Protected members of the base class become protected members of the derived class, and the derived class can access protected data in the base class. Cannot access private data, but it can access protected data, and that's why we make that distinction. So private members of the base class are not accessible to the derived class, so they just disappear. So these private members don't chain down. They're there inside, so when I do any of these derivations, those private members are there inside the object, but they're not accessible. You can't see them, so that accessibility doesn't chain down. So if I have a base, a derived, and a derived again, private members of the base are there in the derived, but not accessible to the derived code, and they're there in the derived again, but not accessible to the derived again code. Okay? They're accessible only in that the derived class can call the base's member function that manipulates that base data. So because that base is inside the derived, that data is there, whether it's public, protected, or private. That data is there, but this describes the accessibility. Under protected derivation, public members of the base class become protected members of the derived class. So this is all the same as this, except that public members of the base class become protected members of the derived class. That means that clients don't see those public members of the base, and so this is not an is-a relationship. This is a part of relationship. Very like composition. The only difference between this and composition is that the member data of the protected, of the derived class can access that protected data. They can access data inside that base, whereas a composer can access the methods, but not the private data, not the data in that composed object. So the only thing that changed between here and here is that public members now became protected members. For private derivation, public members become private members. Protected members of the base become private members. Private members of the base are not accessible. So here's what's happening. Think of this chain, derivation chain, of base, derived, and derived again. Under public derivation, all of the public members chain all the way down. All the protected data chains all the way down. So a derived again class can access the protected data of the base because that protectedness chained all the way down. But private stopped. So the derived and derived again can access that private data. Under protected derivation, now public doesn't chain down, but protectedness chains down. And private doesn't chain down. Under private derivation, nothing chains down. So the derived class can access the protected members of the base, But now that becomes private, and from then on, it's not accessible. For a drive to GAN, can't see that. Okay. So, I don't think I've ever used protected derivation, but I have used private derivation a very, very few times. And if you take design patterns, you'll see an example. An example called the adapter pattern, where we use private derivation. Here's an example. This is a graphics editor, let's say. And so the graphics editor consists of a display list, a list of all these graphics objects, and the graphics objects can be lines and circles and polygons and so on. Now, because this is, let's suppose this is a graphics editor in a CAD application. So from the display list up, there's 10 million lines of code. Now, without polymorphism, the display list would have to say, if you're a line, draw like a line. If you're an object, draw like an object. If you're a circle, draw like a circle. If you're a polygon, draw like a polygon. And so all that code up there says, if you're a circle, draw like a circle, okay? Or move like a circle or whatever. Now, if I add a new object, I break all that code. And I have to find all those places in 10 million lines of code where those objects are accessed. But if I use polymorphism, so now I have a base class and these derived classes, and I make those methods virtual methods, okay? Now, the display list doesn't have to say, if you're a line, draw like a line. It just says draw. And it dispatches, if I'm pointing to a line, it dispatches to a line draw. If I'm pointing to a polygon, it dispatches to a polygon draw. So the display list just says draw, 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 draw. And now I can add a star, just in case I want to put stars on my diagram that I'm drawing. Okay? So, nothing changes. If I didn't use virtual methods, and I add a star, I got to go, I got to go up here and fix all that code that now, not only, even if that code doesn't use stars, the layout of those methods now changes, and I got to recompile all those 10 million lines of code. Recompiling Linux, which is about 20 lines of code, I'm told takes about 3 hours. So you don't want to recompile routinely 10 million lines. You don't. Okay. So that's what polymorphism is all about. Polymorphism means many shapes, and all it really means is substitutability. I get to substitute, so I pass in into a function that wants a soldier. I can pass in a sergeant, a general, a corporal, a major, whatever. Okay, and the function doesn't care. Substitutability. And the same thing is here. I can add a new object, a star object. My display list doesn't care. It just calls move. It calls draw. Whatever. Yes. So public inheritance is a. Private inheritance is part of. Protected inheritance part of. So these words say what we said when we looked at the diagram. Initialization sequences are critically important. So so most of what we've been doing this morning is mental model. This is not mental model. This is a detail commandment. Okay. So I have a class D that publicly derives from B, and its data members, it has a reference member to a stream. Reference member means I don't own this. Somebody else created it, okay? And I have a size, and I have a pointer to an array. The correct way to write the to write this constructor is, here's D accepting the stream object by reference, the size, and a standard string, because I'm going to assume my base class needs a string to be constructed, or can take a string to be constructed. It might take other things, but it can take a string. That's what this assumes. That's what I said here. It takes a string. So now, here I say B of S. Construct the base object. B. B of S. S is the string. S is a string. Okay. So B of S, construct that base object. Out. So this is my reference member. I'm constructing with this out. And this is a reference set. I could not remove this and assign out to underscore out in the body of this constructor, because that would be an attempt to reset that reference, and that's not allowed. C++ references can't be reset. That construction happens on all these things between the end of this paren and the beginning of this curly brace. Whether I make those calls or not, all those guys are constructed in the short flight between this paren and that open curly brace. So before I ever get into the body of this function, that's constructed, and that's constructed. Language guarantees me they have to be. Okay. So this is called an initialization sequence, and it only applies to constructors, initializers, okay? A constructor is an initializer. Initialization sequences only apply to constructors. Yes? Jennifer?
Jessica.
Jessica.
Can you put the size of the arrays inside the curly brace?
Yeah. I could put that there. My preference and your preference should be always to initialize with an initialization sequence if you can. Occasionally you can't, either because there's too many things to do. It's too complicated. You've got to do a lot of stuff that won't fit reasonably in that, Or, there's occasionally, I may have declared this here, I may have declared this here, but maybe this guy needs this for something it does. I don't know why it would, but, and so, they're constructed in that order. So, but whenever you can, which means almost always, initialize with an initialization sequence. If you look at my code, you see me use initialization sequences with my constructors all over the place. So what's happening here is the constructor absolutely will construct my bases. It will construct my bases and my data members. Guaranteed that the compiler will construct them. You can't make it not. There's no way to do that because of that inclusion model. Okay? The base is part of the drive. So they are going to be constructed, but you get to choose how they're constructed with this initialization sequence. I'm calling it a constructor. I'm calling this is really a reference setter, but, and here I'm calling it, this is I'm constructing this array. So I'm telling the compiler how I want them constructed. If I didn't do this, then the compiler would just give me a garbage pointer here. I could come in the body. For that, as Jessica said, I could have in the body, I could have said it, but prefer to do it in the initialization sequence if you can. Why? Because it's a good habit to have. It keeps you out of the bad habits of letting the compiler make the choice for you, and occasionally that choice is wrong. If I don't have any, if all my bases and data members have correct construction, assignment, and destruction semantics, then, and I haven't provided, because I haven't provided any, then the compiler's choices are always correct. But if I start to provide them, the compiler's choices are not always correct. It turns out the command to the compiler can be ambiguous. And so it'll make a choice and it may not be the right choice. So I'm going to show you in those demonstration programs of a case where that's disastrous but happens, which you can always avoid by using an initialization sequence. Okay, so here's another no, okay, this is not enough. This is just what I said. So here's yeah. So my methods in this base class, I can qualify them as non-virtual by not using the virtual qualifier, or as virtual, or as pure virtual. Pure virtual is coming up on the next slide. I should have waited till the next slide. It'll declare the method as equals 0. And what that means is if my method in the base class is not virtual, you should not redefine it. Unfortunately, the compiler, the language will let you, but you should not, because you'll get behavior you don't expect. You can call a base object on a derived method on a derived object that has provided a function for that. Okay. If it's not virtual, there's no virtual function pointer table. There's no slot in the virtual function pointer table for that function. So if I use a base class pointer, I'm going to get for a non-virtual function, guaranteed I'm going to get a base class function, even though you define that function in your derived class. Okay. So I can provide non-virtual methods, virtual methods, and pure virtual methods. So with non-virtual methods, the designer is saying, don't change this method. For virtual methods, the designer is saying, you may change it, but don't have to. For a pure virtual, the designer is saying, you have to. Okay? Good. Designer's got a lot of freedom, and that's good. So here is what this page is devoted to something called double dispatch. So when I pass a soldier, into a function that accepts a pointer or reference to a soldier, when I pass in a general or a private, I'm dispatching to that type, meaning I'm using the virtual function pointer table on a salute call inside that function to decide which function I'm going to call. I'm dispatching to the virtual function defined for that object. I can double dispatch in the following way. Suppose I had more than one display device, and here I have VGA displays and target displays. Now, this shows my age. Target displays haven't existed for probably 20 years. Okay. It's an old slide. I made this up a long time ago. So, assume that one of them is default and the other one is NVIDIA. Okay. Now, when I call list of I, this is just the list guy thinks that's a graphics object. He dispatches to the draw method based on the object that this pointer is pointing to. So he dispatches this point. So he dispatches to the draw method. But now, because I'm passing in a display device, this draw is dispatching to the right device. Double dispatch. And so now, if I provided a default, it's just going to use the normal graphics processing in using the device driver for your display, blah, 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 blah. But if your machine has an NVIDIA display, now I can dispatch to that NVIDIA display, and now my code in that function is gonna use calls on this display device. So if I have a default device, these are just, probably empty functions. But if I have a NVIDIA display, now I got a lot of tinkery code that lets me blast high resolution, very quick stuff. Bam! So I would do this when every microsecond counts. If I'm building games or money market trading software, you know, where a second can be $1 million. Okay. In this, you know, in this automated trading world, things happen in a in a nanosecond. You know, that's why Bloomberg and Fidelity and Goldman Sachs and all those guys want C++ programmers because they want to write really fast code. Okay. Abstract class. So here comes my pure virtual function. Anytime I have a pure virtual function in a class, in the base class, I can't create an instance of that class. And that's probably correct for this application. I don't want to create a graphics. I want it to be a line or a circle or a polygon or something. Okay. So anytime I have a equals 0 on any method, and I can even put it on a virtual destructor if I wanted to, okay, the compiler will not allow me to create an instance of that class. It'll say, can't create an instance of an abstract class. Works just like in C#, we say abstract. We qualify it as abstract. In Java, we qualify it as abstract, right? You Java program? Yeah, okay. Now it says yes. I write a little bit of Java, but not enough to, you know, I haven't written any in several years. So, and you'll find, for example, in the XML element class, you know, the class hierarchy, I have an abstract XML element base class, and it has some pure virtual functions in it. So you can't create an abstract. But you can create a tagged element, or you can create a comment element, you can create a declaration element, all that good stuff. So this just says that. Finite state machines. So polymorphic dispatching turns out to be a nice way to build a state machine. You know, if the state machine is small, you can write it with a, you know, 10 lines of a case statement, bam, you're done, and you know, you wouldn't do this. But as the state machine gets a little bigger and the processing, the state functionality gets a little more complicated, using implementing a finite state machine with a class hierarchy is a great idea. Very often in this is an elevator, and it's just a simple little demo. So, so my elevator, if I'm on the first floor, if I hit the up button, I transition to the going up state. And when I've arrived, I transition to the on second floor. If I hit the down button, I go to going down, and when I arrived, I'm on the first floor. This is an elevator that only has 2 floors. Okay? And so I have all the methods, up button, down button, and arrived. They're all here in the interface. But what the on first floor would do would be an empty down button, an empty arrive button, but an up button that transitioned to going up. Okay? So really simple, and very typically the public interface of the base state class is just the events that can happen. In this case, you know, up button clicked, down button clicked, arrive event happened. Okay? Very common. The code analyzer that some of you have been running on your code before you submitted, I use a state model for the tokenizer. It's got states like eat white space, eat alphanum, eat C comment, eat C++ comment, eat double quote, eat single quote. Okay, each of those eat functions either throw stuff away, the eat white space, or return a token. Okay. Members not inherited. So, so we inherit all the public members except for constructors, destructors, and assignment. So this is copy and move, copy and move, and destructor. Those are not inherited. None of the constructors are inherited. The destructor is not inherited. Neither of the assignment operators are inherited. But the compiler will generate them always. So what that means is that all of the public members are available on the derived class, either because they're inherited or because the compiler created them. In a sense, it really doesn't make sense to inherit a constructor, because in the derived class we got some additional data that almost certainly you got to do something with, and so it doesn't make sense. And it would be a source of bugs, because you'd inherit it and then you'd forget to change the data. So all right, so we're guaranteed that a derived class has all the public methods of the base class, most through inheritance, these few because the compiler will generate them. And this just restates the rules you already know. If it's a void constructor, the compiler will generate one if and only if no other constructors are declared. Suppose you want a default void constructor, but I've provided a promotion constructor. So the compiler won't generate that default constructor for me because I provided a promotion constructor. But I can declare the default, I can declare the void constructor, and I can say equals default, and I just tell the compiler, go ahead and create it. Even though I have one, go ahead and create it. Okay? And what the default always does is member-wise construction. Base-wise and member-wise construction. Okay. And default moves, basically what happens here is if I haven't provided any, so if my class provides all of the correct, my bases and my members of the class have correct construction, assignment, and destruction semantics, then the compiler will generate everything, including move operations. And what they are, when the compiler generates, it's just member-wise. So let's suppose I construct some object of this class that I'm building. I haven't provided any constructors, but I have data members and I have bases, and now I return it out of this function by value. Now, that's a temporary, because as soon as I leave that function, it's going away. Okay? So the compiler says, okay, it does defines a default move, which just goes across all the bases and say, move this base, move this base, move this base, move this member, move this member. So it's just using the semantics of the bases and the members to move. And you do get a move. And if I supply almost anything else, the compiler won't generate move operations. If I supply a copy constructor or assignment operator or destructor, the compiler will not generate the move, because it's saying you're providing those because there's something that some special handling that one of your bases or members need, and it doesn't know how to provide, and so it doesn't provide a move operation. It says, if you have to provide that for your copy construction, then I would have to do the same thing for move, and I don't know how to do that. So it won't. I think, I've forgotten, but I think the rules are, if I provide a void constructor, default constructor, and nothing else, it'll supply the move operations. I'm not sure. There's a really nice book by Scott Myers called Effective Modern C++. And he talks about all that, and he gives you all the rules, just in case you're interested. Okay. So I'm going to stop here with this presentation because I stopped here with the other class. On Thursday, we're going to begin talking about multiple inheritance. And multiple inheritance is funny. Was there a question?
Are you allowed to change return types when you are invoking a void, invoking a virtual function?
You're not changing the return type. What you're so are you saying if I have a virtual method in the base, am I allowed to use a different? So you can if it's covariant. What that means is if my base function returns a pointer or reference to a base, then my derived class is allowed to return a pointer or method to the derived. But that's the only kind of change you can make. You can't make any others. Otherwise, it wouldn't be virtual. Okay. And I don't think I've ever needed to use the covariant return types. Okay. Because normally polymorphism is working for you, and so you're really happy to have that base pointer. If I pass something in with a base pointer, why wouldn't I want to get something out with a base pointer? Okay. So I'm going to stop here from this presentation, and we'll pick up here where we left off on Thursday. So let me kill this and see where we are. So I want you to look at these. I'm not going to dig into these because we will look at that on Thursday. Our agenda for Thursday will be to finish this presentation and look at these two. That's our prime, we may do a couple of other things, but that's our prime activities for Thursday. We got a few minutes, and I want to use that let's use that here. I want to talk a little bit about design principles. So there's several topics: casts, exceptions, and these design principles, where I basically talk whenever there's a little slot available to me. So this is a quick survey of design principles, that is, ideas that should guide your design. And on Friday, I'm going to talk about my design of Project 1. And I challenge you to print out this, bring it with you to the help session on Friday, and grill me about whether I satisfy these principles. Okay? My goal always is to satisfy them. The first and probably the most important is the single responsibility principle. Each software entity, function, class, package, module, where a module is a collection of packages that work together to do something, like the scanner in our parser has a tokenizer and semi-expression. Okay? So it should have one responsibility. That makes designing, testing, maintenance easier because it makes comprehension easier. And we expand on this principle in note 7 down below. I think that's where I expand on it. Encapsulation principle. So encapsulation restricts access to a class's data to class's private data, class's data, to member functions of that class. This means that for well-designed classes, all transformation on the state's data class's state result in valid data. The designer can't guarantee that if the data isn't all private. Even if it's protected, occasionally we use protected in derivation, but even if it's protected, the designer of the base class can't guarantee it, because now a derived class can come and do something totally inappropriate for that data and render it into an invalid state. Okay? So, We provide encapsulation by making all of the class data private. A weaker form of encapsulation allows some of the class's data to provide protected access. That means that derived classes can also have access to protected data. So a correctly designed class may break if a derived class treats the protected data inappropriately. Least knowledge principle. So most method calls are a form of client-server interaction. So the caller is the client, the function is the server. Client makes a call on the server, and the server service does some computation and returns a response. Here, the client and server should be could be a method of an instance of one class invoking a method of an instance of another, a method of an instance of a class in one process invoking through IPC, a method on an instance of a class in another process, a method of an instance on a class in a process on one machine invoking through a proxy, a remote procedure call, or some other form of TCP stack communication like sockets, to a method on an instance of a class hosted in a process on another machine. Ideally, the client knows only the service interface and needs to know nothing about the service implementation. What that says is that your interfaces, whether it's a function interface or class interface, shouldn't require the user to understand the design. Okay? That's why we have private functions. So in my datetime object, I had a ctime function that absolutely requires design knowledge to use correctly, and it's private. I didn't expose it. So there are just methods that allow the user to manipulate datetimes without ever understanding the internal design. Okay? This is the least knowledge principle. We expand on this in note 9. Value semantics principle. C++ language directly supports implementation of classes whose instances have value type behavior. That means we can assign the state of one instance to another instance with the result that the instances have, at the moment of copying, the same state, but they're independent states. They can take their independent way. Java and C# do not do that. If you assign handles, now you get two handles pointing to the same instance. This guy changes the instance, this guy sees the change. And that may not be what you want. We implement value behavior by providing correctly implemented copy constructors, overloading assignment operators, and providing correctly implemented destructors. So those, the methods that we've been harping on, those constructors, assignments, and destructors are at the heart of providing this value behavior. Value behavior means an instance of your class behaves just the way built-in types behave. We can also, using C++11's move construction and move assignment, make changing ownership of an instance values very efficient, blah, 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 blah. All of this is demonstrated in a simple way in the presentation on abstract data types. That's what we looked at. That's the string class. Scope-based resource management principle. So some of these are like single responsibility and encapsulation principle and least knowledge principle are language agnostic. Value semantics is absolutely C++ oriented, okay, because C# and Java don't provide for value semantics other than on the primitive types and structs. Scope-based resource management principle. C++ language has this very elegant mechanism for managing allocation and deallocation of resources to instances. Resources are allocated in a constructor at the site of the declaration of an instance, may be augmented by allocations and other methods, and are deallocated using the class destructor at the end of the scope in which the instance is declared. That means that users don't have to participate in that memory management at all. All they do is construct the object, use it. When it goes out of scope, the class itself takes care of all of that, returning of resources, and the user doesn't have to worry about it. So it means one person has to know how to do that correctly, the designer of the class, using the techniques we're talking about. In C# and Java, we have dispose methods that support timely deallocation, unreleasing locks and file handles and all this. But everybody who uses your class has to know to call that dispose method. Everybody. So we've substituted one person needing to know for everybody who uses it needing to know. And that doesn't sound like a good trade-off to me. Let's go off substitution principle. That's what we've been talking about this morning. Yes, 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 yes. So let's go off substitution principle says functions that use pointers or references statically typed to some base class must be able to use objects of classes derived from the base through those pointers or references without any knowledge specialized to the derived class. Without any knowledge specialized to the derived class. Extraordinarily valuable. This is what lets us build very flexible software. Open and close principle. We should strive to extend or wrap existing code rather than changing the code to meet new requirements. So here's how it's stated. Software entities, classes, packages, and functions should be open for extension but closed for modification. Now, that's a very strong statement. In fact, it's impossible to completely achieve. There's times when a requirement forces us to change something. But our goal is always, if we can possibly do it, rather than change code to meet a new requirement, we wrap it, or we build an inheritance hierarchy that allows us to drive a new class, or we use a template that allows us to put in a new template type. Okay? Open and close principle. So let's suppose 10 years from now you say, hey, I'm a smart guy, I got lots of good ideas, I'm going to start up a new company. Okay? If you don't manage this very, very well, you're going broke in a hurry. If you let the guys go in there and tinker, and here comes a new project, tinker, 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 new project, tinker, pretty soon you got this massive code that nobody understands floating all over the place that has overlapping functionality, and blah. Okay? Dependency inversion principle. I'm going to wait on the dependency inversion principle. We're going to talk about that a little later on. So let me wait on that, because just to properly explain this takes a diagram or two. Interface segregation principle says you don't want to take a class that has many different clients that want to do different things with it and keep extending the public interface. So I got public interface, this part of the public interface supports clients in category A, this part of the public interface supports clients in category B, this part of the public interface supports clients in category C, because that means if category C wants me to add some more functionality, I add it, everybody has to recompile. Because as soon as I add to that interface, the layout of the code changes, and everybody's got to recompile. And you say, Visual Studio, it's 3 seconds, big deal. But if it's 10 million lines of code, which your startup pretty soon will have 10 million lines of code, okay, 3.5 hours, that's a big deal. And you get to go broke. Only 1 in 10 startups survive. if they manage code, it would probably one in 8 survive. Okay, so there's a lot of factors, you know. Some of it is code structure and the way we write code, but a lot of it is other things, capitalization, and did we treat our customers well, and you know, is this a fantasy niche? There really isn't a market there, and all that sort of stuff. Or we have this business model that says, I don't have a clue about how I'm going to make money, but it's great. Let's go into business. Okay. So, all right, I'm going to stop here. So on Thursday, we're going to pick up with the finish the hierarchy presentation, and I would like you to take a peek at these 2 bodies of code, because we're going to walk through them, and it'll mean a lot more to you if you've peeked at them. Okay. If you don't peek at it, I'll walk through it, and it'll just kind of just go right across your, and you know, but there's important stuff that I'm going to show you that if you don't use an initialization sequence, you can have disastrous consequences. All righty, see you all on Thursday. There will be a help session on Friday. Did I say that? There will. Yes, I think I said it. There will be a help session on Friday. And I'll talk about Project 2, and I'll talk about my solution to Project 1. I won't post my solution to Project 1 until next Tuesday, a week from today. But I will then. And if you're one of those people who's asking about where are the videos, they were just put on a place where I can access them last night. And so I will put them up on Wednesday. So on Wednesday, you'll find them on YouTube.
Professor, for the initialized list syntax, so everyone list after the column of the derived class, so they will call their copy constructor?
No, it calls whatever constructor you tell it to call. So, for example,
if it's as
no, look. Whoops, wrong one. We were just looking at that. Let's just go up here. Just go away, Norton, go away. Versus 687. I'll get to it in a minute. I should have pulled up the PowerPoint so a little quicker to. It's coming. Here.
Yeah, just
That's not a copy constructor. I'm constructing a base object from a string.
how about this too?
This is really not a copy construction. What I'm doing is setting a reference. So there really isn't a copy being made. This out, I'm passing in by reference, so it's really a pointer.
Yeah.
And I'm setting my internal pointer, that pointer. It's really, you know, it's object syntax, but it's really a pointer. I'm setting that pointer to be equal to this pointer.
So there
Okay.
will be point to the same.
They'll point to the same one, and that's what I intend. This says I don't own it. You passed it into me. I'm simply using it.
So what if the size is your own defined class? So if we use it in this way, so will it?
It may, you know. So there are if I use copy syntax, so this is like a copy syntax,
Yeah.
then that would be a copy construction. This, because it's a reference, is not a copy construction. It's just a resetting of the reference. It's a setting of the reference.
So it depends type. So it depends the type.
Well, you know, I mean, so if it has copy semantics,
Yeah.
then it's either a copy or I'm setting a reference, depending on how I passed it in. If I passed it in as a reference, I'm setting the reference. If I pass it in by value, I'm making a copy.
So if here I pass a value, not a reference, so
Then,
so if this is
then I couldn't have a reference here. It wouldn't accept it. But
So can I just it's not offstream.
Well,
but
actually, it
it's a
would.
normal.
Actually, it would, except that I think. But
If
anyway.
it is a normal.
But anyway, the point is that these are not necessarily copies. They may be but you are just invoking however you want that object initialized. You're telling the compiler this is how I want it initialized.
Yeah.
That's all.
If it's a reference small a and then I pass a just a, so is it